Today we'll be solving a couple of problems on heat exchangers. First thing is how to use your data book. First you go to the index page and search for this tab on heat exchanger, and this page number that you see here, go to that page in your data book. You can pause the video and go to that page, and once you land on this page, the first thing that you have to read or you have to learn is this formula: Q equals U A delta T LM. Now first you need to understand what the symbols are. Q stands for the heat transfer rate in the heat exchanger. U is the overall heat transfer coefficient, and A is the heat transfer area, and delta TLM is called the logarithmic mean temperature difference. So this is the first and the most important formula in heat exchanger design. This is called the LMTD method. In the LMTD method, the fundamental equation is Q equals UA delta TL. And here you see the LMTD for a parallel flow configuration and LMTD formula for a counter flow configuration. Now coming to the notations, we know Q is the heat exchange, that is the heat transfer in the heat exchanger. U is the overall heat transfer coefficient, and if you want the overall heat transfer coefficient relation for them, you can see them on the page number given here. And delta TLM is the logarithmic mean temperature difference, or in short LMTD. A stands for the heat transfer area in the heat exchanger. Now these are the temperatures. In the data book, the notations given are capital T1 and T2 stands for the entry and exit temperatures for the hot fluid. So for the hot fluid, you use an uppercase T, and for the cold fluid, you use a lowercase t. Okay? So now I would like to show you a simple heat exchanger in parallel flow configuration and the temperature profiles. In parallel flow, you know that, let's say the hot fluid flows inside and the cold fluid flows outside. Let's say this is the cold fluid. So this is T1 and T2, the cold fluid entry temperature and the cold fluid exit temperature. And this is the hot fluid entry temperature and the hot fluid exit temperature. Because they are in parallel flow, both the fluids are flowing in the same direction. This is the cold fluid and this is the hot fluid. Now if you look at the temperature profiles within the heat exchanger, let's say this represents the distance along the heat exchanger, along the length of the heat exchanger. I'll use a red color for the temperature profiles for the hot fluid. The hot fluid comes in at a temperature of T1. The temperature of the hot fluid decreases as it flows through the heat exchanger, and it attains a temperature T2 at the exit of the heat exchanger. And this is the direction of flow. Now, if you look at the cold fluid, if we sketch it in blue, the cold fluid comes at a temperature of T2 into the heat exchanger, and it comes in at a temperature of T1, lowercase t1, and its temperature rises because of the heat transfer that is taking place, and it exits at a temperature of T2. So this will be the temperature profile for the cold fluid. In a parallel flow configuration, you should remember that this temperature difference is what is driving the flow. So this delta T is what is driving the flow, and at the exit, you cannot have the exit temperature of the cold fluid to exceed the exit temperature of the hot fluid, which means the exit temperature of the cold fluid should always be less than the exit temperature of the hot fluid. The cold fluid exit temperature cannot go beyond the hot fluid's exit temperature in a parallel flow configuration, because what is driving the heat exchange here is a temperature difference. And if the heat exchanger is infinitely long, let's say if x tends to infinity, only in that case T2 will approach capital T2. The cold fluid and hot fluid exit temperature will be equal. You cannot have an infinite heat exchanger in practice, and even if you have an infinite heat exchanger, the exit temperature of the cold fluid cannot exceed that of a hot fluid. This is something that you have to remember for a parallel flow configuration. Whatever I have sketched is for a parallel flow. Now if you look at a counter flow heat exchanger, the same double pipe heat exchanger, I am sketching the temperature profiles directly. Say this is the entry and that's the exit of the heat exchanger. Now if you look at the hot fluid's temperature, it comes at temperature T1 and the temperature of the hot fluid continuously decreases, goes to T2. Now if you look at the cold fluid is entering the heat exchanger from the other side and its temperature rises. So basically T1 is here, the cold fluid entry is here in the opposite direction to that of the hot fluid, and its temperature rises. Now because of this direction, the change in direction, you see that the temperature difference that is driving the heat transfer is this, delta T. And you observe that now the temperature, the exit temperature of the cold fluid, which is small t2, can exceed the exit temperature of the hot fluid. So here T2 can be greater than T1, greater than capital T2. That is, the cold fluid can leave at a temperature higher than that of the hot fluid that is leaving. And when this is true, you know that if the cold fluid exit temperature is greater than the hot fluid exit temperature, definitely it is a counterflow configuration. It cannot be a parallel flow configuration. Continuing with the symbols that we had, MC represents the mass flow rate of the cold fluid in kilograms per second, and MH represents the mass flow rate of the hot fluid, again in kilogram per second. And CH and CC are the specific heats of the cold fluid and the hot fluid. I think in my data book there is a mistake. CH stands for the specific heat of the hot fluid and CC stands for the specific heat of the cold fluid, and the units to be taken are joule per kilogram per Kelvin. Take it in SI units. The fundamental relations in a heat exchanger are three. The first one we have already seen. This is printed in the data book on the top. Q equals UA delta T Lm. This is the basic equation in the LMTD method. In the LMTD method, once you know the LMTD, you can multiply it with the area and the overall heat transfer coefficient and you will get the heat transfer. Now if you look at the basic flow of heat in the heat exchanger, what is heat doing to the hot fluid? The temperature of the hot fluid is decreasing because of the heat transfer. So we can write Q, the heat transfer in the heat exchanger, equals MH CH delta T for the hot fluid. Okay, this is for the hot fluid, and for the hot fluid we are using a capital letter. So I can write it as MH CH. Because the hot fluid temperature is decreasing, I am writing it as T1 minus T2. So this will be 1, let's call this as equation 1. Q equals MH CH T1 minus T2. This is a lowercase c. There's an uppercase c, so I'll be careful here. So this relation, let's call it as equation 2. This is the heat transferred from the hot fluid, and because hot fluid is giving away this heat, its temperature is going to decrease. We can write a similar equation for the cold fluid. Now I am assuming that whatever is the heat from the hot fluid, it enters the cold fluid. There is no heat loss from the heat exchanger. If we make that assumption, I can write that Q is equal to MC Cc. The temperature difference in the cold fluid, this will be T2 minus T1 because the exit temperature of the cold fluid is higher than the exit temperature of the hot fluid. So I am making Q as positive quantity by writing the greater temperature minus the lesser temperature. Now these three are equations that we can use in heat exchanger in LMTD method. The equation 1 is particularly for the LMTD method. 2 and 3 can be used anytime. But you have to assume, here we assume that whatever is the heat transferred from the hot fluid is equal to the heat transfer to the cold fluid. I am assuming that the heat exchanger is well insulated, so there is no heat loss from the heat exchanger. Under these assumptions, we can assume that Q is the same. The heat transfer from the hot fluid is same as the heat transfer to the cold fluid.